Greetings, ladies and gentlemen. Thank you for coming in for today's session. Kind of a tutorial today. What we are going to do, we are going to take a look at one final exam, go through it, and then take a look at a few quiz questions we had in the past week. And through the process, you would know what the expectation is in the final exam. Now, the course itself is enjoying a special benefit and property, and that is we talk about different techniques, but the circuits we are studying in this course are all linear circuits in one sense. And because they are not behaving strangely in terms of both frequency and in terms of time, what happens is that if you consider that circuit and you approach solving that circuit using mesh, nodal, superposition, source transformation, Thevenin, Norton, often you are supposed to get the same answer. So the property this one gives us is the benefit we are going to have from this property is that if you pick up a given circuit from chapter 10, chapter 9, chapter 11, chapter 10 mainly, and then you consider studying that circuit through different techniques, you're supposed to get the same answer. So if you don't have the answer at the end of the textbook, no worry. If you don't have access to a TA, no worry. If you don't have access to the instructor, you don't have to worry about it, because from a probabilistic point of view, it is really rare that you are going to have the same answer for the same circuit if you consider 3 different techniques. That's the benefit. It allows us to have a self-assessment even inside a final exam. 4 questions, as you can imagine, both in the midterm and the final, enjoyed the benefit of similar answer, equal answer at the end. So you would know by the end of the 4 questions whether you are on the right path or not. That's one property of this exam. We are, for example, this is the question from July 2010, and we are going to solve these questions 4 times, and we are supposed to get the same answer. The other issue that I need to raise here is that the exam is comprehensive, which means that it is trying to encompass as many topics as we have. That's why this exam and previous exams and this term exam is going to be a 9-question exam. It's going to cover almost everything you have learned in this course. So even though we are going to solve a simple one, a sample one today, it doesn't mean that you got the first-hand exposure to the exam questions. What takes you to the finishing line is exercise. One of the pitfalls I have seen in midterm in this class and previous is that some of our friends think that if they pick up a midterm and a final and they solve that midterm and the final, they would be ready for the exam. That's not the way it is. You need to pick up a question from a chapter 10, for example, and you need to handle that a number of times from different angles, from different techniques. And then you need to move on to the next one. And you need to find where the mistakes are. If you find where the mistakes are, then you would be educating yourself. There is nothing better than learning from your own mistakes. As I have said previously, instructors would be only 10% of your success, maybe 20% of your success, but the majority, the major part of your success depends on you picking up the pen and writing the solution on a paper and checking it first individually. Please do individual work. Then work as a team, find your friend, and then brainstorm the solution. And then basically check the solutions we have posted on the blackboard. And that's going to take you a long way compared to just sitting inside the class and having a very nice and sweet session. That's only it is. And after that, it is all hard work in that sense. The last thing I want to remind you of is that this exam is a speed exam. Although we are facing a huge challenge in terms of complex numbers, only those who have exercise would be able to get to the finishing line. So the exam typically 9 questions, 3 hours, gives you 20 minutes each question. And imagine that you might have some mistakes done, and imagine you need to come back and you need to fix it. Imagine the confusion you might have if you don't have enough exercise. With the exercise, I guarantee you, you are going to be in a very comfortable position, except if there are some other elements involved, for example, the stress of the exam or so. So what we are going to do today, I'm going to take away as much possible stress from you as I can. I want you to feel comfortable what the questions are going to look like, although it's going to be covering almost everything we have discussed inside the class, and sometimes a question or two might be changing here and there. But generally speaking, that's the way we are going to approach the final exam. So here is a question. The first question, we have the same circuit for 4 of the questions we have. You have to pick up a few important vibes from this design. First, do you have only one capacitor inductor? Well, of course you have more. You have an inductor and a capacitor. This is therefore a second degree design. If you remember, chapter 7 was about first degree design. So if you have more than one capacitor inductor, immediately you're out of chapter 7. You're into chapter 10. Another indication that you're in chapter 10 is the excitation input. This one is a sine cosine function. This one is a sine cosine function. In front of you, you are dealing with chapter 10, which requires an AC response. Another thing you need to pick up from this design is this. Are you in time domain or are you in frequency domain? Take a look. You have a T and you have a small letter, a small case for VO. So that tells you you are in time domain. Of course you can solve this using differential equations and second degree differential equations and even presenting to us the transitional response. But in chapter 10, all we care about would be the steady state response of this design. We had an algorithm discussed last time, and the algorithm says, take the design, piece by piece, element by element, take them into the frequency domain. Then you are going to have this entirely in frequency domain. The benefit of that domain is even a capacitor then behaves like a simple resistor. It's going to be a complex resistor in one sense. And then since everything is kind of resistive to us, we can benefit from whatever we have learned before the midterm. Series component, you can shrink them. Parallel components, you can shrink them. If you have to do basically circuit reduction, you can do it. Everything is possible when you go into the frequency domain. So the first thing I like to do is to take this to the frequency domain. One of the assumptions we made is this. Although you have a bunch of input excitations, so for us 4 cosine 4t or 32 sine of 4t, we made an assumption in this class, and that is the incoming signals are supposed to be presented in cosine format. This is cosine, I'm happy. The coefficient is positive, I'm done. This one is not cosine, and I need to take it to the cosine domain. So this one I know, and this part you have to know it from heart, and that is this one going to be 32. Actually this one is too small, it may not be visible, so I'm going to continue with the black. 32 cosine 4t minus 90 degrees. If it is positive, this is minus. If it is negative, this is plus. So if you don't remember this rule, all you have to remember is a very simple formula. The formula says cosine alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Okay. This is plus, this is minus. If you had it minus, again this one doesn't work. If you had it minus, this one is going to be plus. So it's opposite in one sense. Now, if you want to have a minus sign represented, then it would be plus 90 degrees. Because if you say plus 90 degrees, cosine 90 degrees is 0, you have no body on this part. Sine of 90 degrees is going to give you 1, minus sine alpha would be cosine alpha plus 90 degrees. If you want to have a plus sign, all you have to do is to have this minus inside. So it would be minus beta. So if you have plus of sine alpha, it would be minus 90 degrees. That's the way you will see it. You can map this simple equation into this scenario. It helps me to take care of both sine and plus minus sign that is basically behind the component, the function. Okay. The next thing I need to do is to take them into the frequency domain. And remember, generally speaking, if you have a cosine basically alpha plus theta, actually I want to replace this alpha with omega t. Remember the rule we had? The rule is take this into the frequency domain. Amplitude, provided it is positive, is going to be A, and then it's going to be angle theta. So it's going to be e to the power of j theta. This is a polar representation. This is called a phasor. It's just a different naming. Phasor is the same as the polar representation. What happens to my omega t? Remember, we capture this critical information and we write it down on the side. So omega is going to be equal to 4. I am conscious. I see that these two omegas are the same. Since they are the same, the entire system is going to work around that frequency. So that frequency is going to be in the current, the voltage, everything. That's why I'm capturing it, and I'm going to return it back into the final response when I want to take this system back into the time domain. I'm going to capture it, and I'm going to let it go after that. Now, some of you might ask this question: what happens if this is, for example, is 3t and this is 6t or 7t? What happens if the frequencies are different? You can take them to the frequency domain, but you have to go only through superposition. You have to keep one at a time and take care of the 3t, assuming this is set to 0, and everything else is going to go into frequency domain. Take care of the 7t, assuming that this is 0, and take care of everything in that frequency. So that frequency is the hallmark. That frequency is going to have an impact in the value of this capacitor and the value of this inductor. The good thing is that we are not going to be testing you on this. This is an issue for those who have an interest in higher frequency in some non-linearities and so on. The system is linear. We intend to have the same frequency applied. Here we have 40, we got the 4, we are done. Let's take this now into the frequency domain. 32 sine of 40 is 32 cosine 40 minus 90 degrees is equal to 32 angle minus 90 degrees is equal to 32 e to the power of minus j 90 degrees. And I did this in frequency domain. How much is e to the power of minus j 90? Sometimes it's easy to take it and simplify it. You don't have to do this all the time, but sometimes it's not really that difficult to handle this easily. So remember my unity circle. The unity circle, I hope you can see this blue, has an axis horizontal, an axis vertical, and then this is going, the length of, the radius of this circle is going to be 1. That's why it's unity circle. For 0 angle, you see this is this, and the 0 angle right on top of that is going to be plus 1. Now I want you to think of this arrow and move it. As you move to this stage with 90 degrees, you're going to have plus j. As you continue and you have 180 degrees, you're going to have minus 1. You continue this and you get minus 200 and plus 270 degrees, or in one sense, minus 90 degrees. They are the same. Minus 90 degrees, 270 degrees, I'm going to have minus j. This point, this point, this point, and this point. When I say e to the power of minus j 90 degrees, that's minus 90 degrees, and that's going to take me to minus j. This is going to be minus j. And therefore, I can actually simplify this as minus 32j. That's the number when it goes into frequency domain. How much is this in frequency domain? This one is going to go, the amplitude is positive, the angle is going to be, the frequency is captured, the phase shift is 0, that's going to be angle 0. It's 4 e to the power of j0, and e to the power of j0 gives you +1, and that's going to give you 4. It's better to do this slowly and systematically rather than making a mess later. So I'm going to erase this, and I'm going to slowly map this to the next stage. What have I achieved so far? The incoming voltage source is minus 32J. And please do remember this minus sign. That's one of the simplest mistakes I might do. And the resistor is going to be the same as it goes into frequency domain. The capacitor depends on the frequency. That's why we need the frequencies of excitations to be the same. The capacitor, we are going to calculate that through the special formula for the capacitor. The resistor is going to remain the same. The voltage now is going to be capital V, and then the current source, as we just showed up above, is going to be just simple 4. This 4 is not DC anymore. This is in frequency domain. Remember that. In frequency domain, that 4 actually represents 4 cosine 4t already. Okay, let's go and have this inductor and then to have this resistor. No worry about the resistor because they are going to be mapped relatively easy. Now the capacitor is 1 over C omega J. That's why I need this omega. That's what I captured. 1 over 12, that's my number. The omega is going to be 4, it's going to be J, it's going to be 1 over J divided by 3. 3 comes on top, that's 3 divided by J. And do remember, 1 over J is minus J. So remember, 1 over J, let me write it down, is minus J. Because if you multiply, JJ is going to give you minus 1 and a minus behind, that's going to be plus. So I'm going to say this is going to be minus 3J. The rule of thumb is this. An impedance shown as a negative value in frequency domain is either pure capacitor, or for those who have interest in higher courses later in electrical engineering, it's going to be capacitive, which means it might be a combination of an inductor and a capacitor. But the capacitor is overtaking it. So this shows me the impedance of that component, and that component is capacitive. If it is minus, it's a capacitor. So I need to make sure that I got the right value, minus 3J. Let's go for the inductor. The inductor is going to be L omega J. L omega J. L is 2, omega is 4, and J. So this is 8J. Now you are ready. Take a look at what happened. This in time domain, taken into the frequency domain, and I do see resistor, 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 resistor. Of course this is inductor, but what I mean is a complex resistor. Why? Because the simple rules of resistor we learn is going to be applicable. I'm going to play and apply 4 different techniques on this one. At the end, I'm supposed to get the same answer in frequency domain, the same answer in time domain. So I'm going to solve that in frequency domain 4 times and grab one of the solution and then take it to the time domain. So in that sense, the same circuit you just see underneath is going to be the system I'm going to solve. Now, the first question says, solve this using superposition. Well, we remember the techniques and the type of demand that technique puts upon the design. So if I want to do this superposition, and the voltage I'm asking is actually the voltage of this 1 ohm. Because it's the voltage of 1 ohm, That's the point of interest, remember? I can actually do anything else with that design without harming it. So, for example, I can say 6 and 8J, these are two resistors in series. The topology would be the same. I'm not doing transformation. 8J and 6, they are simply in series, and I'm going to put them in one concept. So I'm going to actually say this is going to be 6 and 8J. Let me not forget 6 and 8J. That's this one. I have seen some who hadn't practiced hard enough to actually, for example, assign a node in the middle of these two. That's actually correct. No harm in that. The harm is the calculation time. Since these two are in series, since I have no interest in the voltage of individual components, I can actually shrink this, reduce it. And if I reduce it, I'm going to get another resistive network. So this one is going to be 4 minus 3J. So this one is going to be 4 minus 3J. And I'm done. This one. Whatever technique I'm going to apply, I have an interest, an eye on this 1 ohm and the voltage across, and I have a bunch of complex resistors in my design. Let's begin. I want to do superposition. Superposition says take a look at the number of excitation inputs and grab one at a time and shut down everything else to 0. If it is a voltage source, when you shut it down to 0, that's going to be a short line. If it is a current source, when you shut it down to 0, that's going to be an open line. So let's do this one at a time. Number 1, I'm going to keep this. I'm going to shut down this to 0. This is going to be actually an open line in my view. So I'm going to have this plus minus 32J, of course, and then I'm going to have 4 minus 3J, and then I'm going to have the voltage across the 1 ohm. I'm going to maintain the same polarity, superposition, the same polarity, but I'm going to label this index 1, which means it's the contribution of the voltage source. And then I'm going to have my final resistive value, which is 6 plus 8J. When I want to take care of this, remember in superposition we ask you usually to draw the two topologies before you attack. You can actually solve each topology individually, but generally speaking you have to have the topologies ready. So I'm going to keep this one in mind, and I'm going to shut down this to 0. That's going to be a short line. That's going to be a short line. It's going to be, this is the second contribution, the second source, 4 minus 3J. It's going to be 1 ohm. The voltage is going to be VO2. I index it accordingly. This is a short wire now. You remember the rubber band? It's going to be the same. So basically, I can actually redraw that for the comfort of my mind as how to see this. This is going to be the next one. 6 plus 8J. I need to find VO1 due to the contribution of the voltage source. I need to find VO2 due to the contribution of the current source. And if I sum them up in frequency domain, that's going to be the response in frequency domain. Now, because I feel everything is in kind of a resistive mode, I can do a lot of things. Here you can do circuit reduction. You have 1 ohm and you have 6 plus 8J ohm in parallel. And you can shrink it. But remember, in the reduction process is this. When you shrink it, what happens to my voltage or current of the interest? And if you are losing that site, you need to actually backtrack it. So in this case, I'm going to say that's going to be plus minus minus 32J. Then it's going to be 4 minus 3J. Then it's going to be another resistor, a complex resistor. This is the conclusion of these two components in parallel. But I also know, because these two are in parallel, because my voltage is the point of interest, I'm not losing the site. The site is still VO1. This voltage is the same as this, is the same as this. The voltage of parallel components would be the same. How much is this value? It's 1 ohm in parallel with 6 plus 8J. I can give you an immediate response just for 2 resistors in parallel. You can say multiplication plus the addition. Only for 2. Remember the G rule. You need to apply the G rule generally. But this one is going to give you 6 plus 8J divided by 7 plus 8J. As we have shown you before in the calculation, and I hope this might be visible, this is a regular calculator. I'm going to keep a bit of a distance so that everybody knows. I'm going to go into mode. I'm going to push 2. I'm in a complex domain. And one thing you need to keep in mind is it a degree or is it a radian? By default, it is in degree mode. So I want to do a division, open bracket, 6 plus 8 times J. 6 plus 8 times J, close bracket, divided by, open bracket, 7 plus 8J, close bracket. If I say equal sign, I'm going to get myself the real part. It's going to be 0.93 or 94 already. So this one, as I do some rounding, I'm going to have minor change of response later. So that minor change of answer is expected. You see, instead of saying 0.938, 0.53 some, I rounded it up. So I do expect when you attack the same system so many different ways, I do expect you guys to get about 5-10% error in the process. That's not a surprise. Okay, now I need to get the imaginary part. You just do shift equal sign and it gives you 0.071. Is positive 0.071 J. I and J would be the same. Okay, what was the intention? The intention was to find this. It's 0.94 plus 0.071 J. You have 2 resistors in series in front of a voltage source. That reminds you of a voltage division principle we have applied before, and that's going to give you a hand. How much is VO1? VO1 is equal to the resistor, in this case 0.94 plus 0.071 J divided by the same resistor 0.94 plus 0.071 J plus the resistor on top, which is 4 minus 3J. That shows me the ratio, but then times the incoming voltage. Time the incoming voltage, so it's going to be minus 32J. That's 1 ohm already. So that's going to give me my VO1. Let's calculate this. Again, because I did some rounding, obviously I'm going to have some issues in terms of calculation. So I'm simply going to say divided, it has an answer already. That answer was with all the accuracy involved, divided by open bracket 0.94 plus 0.71 J. Am I right? No, I'm not right because yep, 71J, yep, you're right. Okay, and then plus continue 4 minus 3J, closed bracket. Okay, I did my denominator. You simply divide. That's going to give you an answer. But I need to multiply whatever the answer I got into minus 32J. So let's write it down. It's almost 3. So this one is going to be 3. And when I say shift equal sign, it's going to give me minus 4.29J. If we are not ready for complex numbers, that's where the major time is going to be consumed. How do you calculate that division? That's what happens. What did I do? These 2 are in parallel. I shrunk it to this one. I used the voltage divider principle. I got the contribution of VO1. That's the VO1 due to this. Because I need a space, I'm going to go ahead and erase as much on the whiteboard as I need to. So this part, I'm going to erase it. Okay, nice and clean. Now let's take a look at the second design. The second design is no stranger to us. You have a current source. You have a resistor, and then a resistor. This is a horizontal, but obviously this is a rubber band in your mind, right? You can grab this and actually you can see that this component is in parallel with everything else. All four components you see in the middle are actually in parallel. And the voltage I need is the voltage of 1 ohm. So here is a game plan I have. The game plan I have is this. This in parallel with this, in parallel with this, that's going to give me a resistor. And since the current goes in, I'm going to find me the voltage I need. So I'm going to say, tell me how much the parallel combination of these three complex resistors will be. I'm going to call this Z equivalent. It's going to be 1, 4 minus 3j plus 1 over 1 plus 1 over 6 plus 8j. If you are going in to simplify this, you'll make a mistake right there. Don't do that. Simply divide it using the calculator. Isn't that interesting? 1 divided by open bracket, 1 divided by open bracket, 4 minus 3j. Remember to put the brackets in the proper place. That's going to separate them. That's going to give you a safety zone. 1 divided by 1, of course that's 1. But that's a silly one. I'm going to do that anyway. And then 1 divided by 6 plus 8j. Whatever the answer is, you need to inverse it. So there is an inverse opportunity for you on this one. It's x minus 1. So I'm going to just push it, and I'm going to ask for the values. My z, remember I did this and then I inversed it. My z is going to be, so let me actually tell you what the shape is going to look like. That's going to be 4 in frequency domain. This one, according to my calculator, is 0.818, 819, something like that. And then shift equal sign is going to be minus 0.027. Although you're writing this for us, you can actually keep this on your calculator because the answer is with all the accuracy stored inside the calculator. So when I want to find this voltage, remember, that's the plan. This is going to go in, hit the resistor on top, creating the plus minus, the same polarity I had, and that's going to be my VO2. The answer with all the details is in my calculator. So all I need is this Z equivalent times 4, and that's going to be my VO2. So what I'm going to do is this. I didn't do anything, although I wrote some 2-3 digits on the white paper for the examiner to see. I simply say times 4. It's going to be answer times 4 is equal to, that's going to be 3.275, and then shift equal minus 0.107J. Okay. You've got VO1, you've got VO2, and superposition is the most extensive, expensive, time-consuming method in the exam. So you need to add them up. So let's add them up and see what happens. My VO total is equal to VO1 plus VO2 because I maintain the same polarity on both contributions. I need to add this, which I still have it on my calculator, plus this, which has some rounding error already. So it's plus 3, open bracket, 3 minus 4.29J. I've got a very good response. 6.275, shift equal sign, oops, I lost it. It's going to be, hold on, plus 4.29, it's 4.4. So it's minus 4.397J. I minimize the human intervention in the simplification of complex numbers. That's where the majority of the mistakes are going to happen. So please utilize your approved calculator. You're not supposed to bring in anything other than the approved calculator. I understand there are programmable calculators where you can actually punch in the number and get the response. Of course, you have simulators for electric circuits where you will just draw a schematic and you get the response. That's not the intention. The intention is to stimulate your mind, massage your brain to be able to produce the same ideas, innovative ideas in the future. Okay, that's my answer. Let's go to the same circuit. I don't want to take this into the time domain yet. I'll do the time domain later. Okay. The same system, I want to solve this using nodal equation. Is it nodal? Yes. Well, the graph is one thing. The connectivity and the show up of the system is one thing. But you need to know what is happening. When I say plus minus VO, and here is my voltage source, and here is my current source, and my rule of thumb is this. If you have only one voltage source, typically the minus pin of the voltage source is going to be your ground. So I'm going to say this is my reference node, or the ground. This is my reference node. This is also my reference node. One end of the resistor is connected to the reference node. The other end of the resistor is connected to this node, which I'm going to call, say, Vx. But since this is connected to this node, I can see that this node versus the reference, this node versus the reference, is actually this versus this. VO is equal to the plus sign minus the minus sign. The plus sign is on top, the minus sign is the bottom, so obviously that connection is made. This connection is going to save you a lot of time. So let's go and write the equation. How many equations do you need? If you have not reduced the two components in series, and you consider the node in between, your system is going to be basically quite huge. But this is only one equation, one unknown. You see, the exam demands that you pick up smart steps. Smart steps is what is going to take you to the next stage. So if this is 0, I know how much this voltage is. That's going to be minus 32J. If this is 0, this is VO, this is VO, this is all VO, I know. So I have only one node to write. It's going to be, I'm going to assume VO is the biggest voltage of the entire design, just for the comfort of writing the equation. I'm going to be a very calm person in the exam. I'm going to put the components that have to be inside the bracket so that I'm not going to miss a minus sign. This minus this divided by this. 4 minus 3J. This minus this divided by 1. VO minus 0 divided by 1. This one is entering the node, so it's going to be minus 4. Then the only component I have is the last one, so it's going to be VO minus 0 divided by 6 plus 8J as equal to 0. I have 1, 2, 3, 4 components attached to the node. When I write the equation for that node, I need to have 4 terms. 1, 2, 3, 4. That's the way you need to easily connect the scene if everything is done properly. Now, you don't have to simplify this. That's the mistake or the time-consuming step that is going to cost you too much. I'm going to just say 1 over 4 minus 3J. Then I'm going to say 1, then I'm going to say, then I'm going to say plus 1 over 6 plus 8J. Remember, I factorized VO. This is constant, it goes to the other end, it's going to be minus 32J divided by 4 minus 3J. This is minus, goes to the other end, it's going to be plus. So this one is going to be 4 plus minus 32j divided. You could practically take a common denominator, but you don't have to, because you can take advantage of the calculator. So let's pick up the calculator and simplifying the coefficient of VO. Open bracket, 1 divided, open bracket again, 4 minus 3j, and make sure that those components, if you don't put this in a bracket, you're going to make a mistake. So this is something you need to practice, and practice until you get it right. 1 divided by 6 plus 8i. Okay, 1.22. So this is going to be VO 1.22, and then I need to find my complex portion of it, which is equal sign, shift equal sign. It's minus 0.4, minus 0.004j. Since you have the answer, you can actually inverse it immediately, because whatever happens on this side, you need to have this go underneath to the next section. So you can actually inverse this because you have the answer on the calculator, and then multiply it by the right hand side. But since you don't want to, let's do it the other way around. 4 minus 32j divided by, open bracket, 4 minus 3j. I make sure everything is in proper order, and immediately it gives me 7.84, shift equal sign, minus 5.12j. You have the answer with all the little bits all the way. All you have to do is divide this by this. Divide the answer, open bracket, 1.22 minus 0.04j, close bracket. This is inside the bracket. When you divide, VO is going to be 7.84 minus 5.12j divided by 1.22 minus 0.04j. Everything is inside bracket, I made sure, and this is going to be 6.556 minus 3.98j. Well, there is a bit of a difference, as you can see, from this one and that one. When you get this much difference, don't panic. This is an expected difference, and the reason is, often in the process, I actually ignored and rounded up the numbers. But I'm going to quickly go and make sure the numbers are okay. So let's try this one more time. 4 minus 32j divided by 4 minus 3j. I hope I haven't made any mistake of that part. Okay, and then divided by 1 divided by 4 minus 3j. I'm actually using this big bracket as the underneath. I don't even simplify this. I'm using right away inside the bracket, and hopefully I haven't done any mistake. Actually, if I avoid this simplification, just this simplification, just hold on now. This one? Yeah. It's a plus sign? It's a plus sign. Thank you. And you see, that part of mistake. I didn't do, the next time I tried, I did not simplify this. I simply punched it. I said, take this and divide by this bracket. And here's what I'm going to get. I'm going to get equal to 6.282 minus 4.402j. Still, you see, a minus, a matter of a small variations that is acceptable. The reason my error wasn't too big, because as one of the attendees just pointed out to me, this is supposed to be plus. I made a mistake on that part. It's supposed to be plus, and I made it minus. So, what I'm trying to ask you to do is simple. Calculate this, divide by this Don't even simplify this. Just punch them in. And you get a better response, a more accurate response. And if you want to come back and see what the mistake is, you can always come back and easily see where the mistake happened. Because your number of steps you took would be smaller. And therefore, if you have a mistake, you can come back. Now, I solved the same system twice. One superposition, one nodal. And I got almost the same answer. This is going to be the guidepost for you. This is going to be the guiding response for you. Someone has given you the answer. That's the angel, and that would be you, right? You found the answer, right? Now, if you want to solve this using mesh, you need to have the same answer. Probability, it's almost impossible to have identical answer for two different techniques. Almost impossible to have it. Okay? And we definitely check the steps to see how you got to the final answer. So that part, leave that to us. But let's go for the mesh. I want to erase this. This is my answer. Remember that, please. I want to do mesh. And hopefully I have a way of not simplifying too much. Let's see if I can do that. Okay. I want to slightly change this. I want to stretch this up and stretch this down so that you can see what is happening. For those of us who have a bit of a challenge in terms of viewing, what is this system? I just stretch this up, stretch this up, and stretch this up, and stretch this up. I'm sure many people would find this interesting and different than the original one. In terms of mesh, we are supposed to identify the basic loops first. So this is one basic loop. I'm going to go and assign clockwise. This one, this two, this three. When I assign three different loops, if I find three different basic loops, no matter what I do, I need to have three loops. There are tons of techniques to approach this, and the textbook has one possible options, but I'm going to ask you, and that's what we did in this class. You have a current source. This current source has been touched twice by this loop and this loop. That's pre-midterm. Okay? Now, I need you to remove one of the loops that is touching this and allowing the current source to be touched once. There is a magic behind this, because if the current source is touched only once, that's going to dictate what the current of the loop is. So if I take this one, for example, I'm just going to go ahead and I'm going to remove this one. Okay. The reason I did that, because I simply wanted to avoid a negative sign. You see this direction going up, this direction is going up. That's why it's a kind of a guiding principle for me to do that. Okay, but you see, you had three basic loops. You got rid of this. You need to give me another one. You need to replace it for me. So, in order to replace it, I could easily use this one. This time, I'm not touching this. But of course, this component now is going to see two loop currents that are going to go through it. Now I'm ready to label it. Remember, if you label the basic loops, when you remodel the loops, the labels have to change because the currents are going to change. So in this case, I'm going to call this I1, I'm going to call this I2, I'm going to call this I3. Because this current source is touching loop number 1, or current I1, and only that, I'm going to declare what I1 is. I1 is going to be 4 amp. Then I have two more loops, and I need to write my KVL law. Let's start from this point for loop number 3. It's going to be, I'm coming from the bottom of the voltage source. I have a minus sign, and I have another minus sign. Minus 32J. Be gentle. Don't be in rush. Write it slowly. Therefore, you won't make a mistake. 4 minus 3J. times the only one that goes in is I3. But when I get to 1 ohm, I have I3 that goes in, that's the master. And I have I2 that comes up, that's the slave. This component is shared between two loops. This is the biggest one, this is the smallest one in that sense. Just for the sake of my writing the equation, is I3 minus I2. I3 is coming as the master, I2 is the slave. And since a slave is actually opposing it, it's going to be a minus sign. And that's it. I have this, three components in that loop, and I have 1, 2, 3 terms in this. So this is multiplication actually. Okay. What is left? Loop number 2. Loop number 2 has this and this. So I have only 2 components to write. This doesn't belong to loop number 2. So let's begin from this end. It's going to be 1 ohm times, now I2 is the master, and everything else is a slave. I2 is taking the lead, and I3 is opposing it, minus I3. Then I'm going to have 6 plus 8j times. Now I need to be careful on this, because not only I2 goes in, I1 is also going in. I2 takes the lead. I1 is the slave. But also I note that these two currents are actually going in the same way, from top to the bottom, to the component. That's why I'm going to have plus. If you did not do this simple modification in the first place, you are going to end up having 3 equations, 3 unknown, if not 4 equations, 4 unknown. So that's the challenge. You see, now I can solve a 2 by 2 system. If you didn't follow this step and you follow the textbook, you solve 3 by 3 system. Of course, you can do elimination of an unknown and make it 2 by 2, but as much as you bring in human intervention, you're going to make mistakes. Okay? So let's do this. The first thing is to write the equation. This part we learned it superbly before the midterm. We learned how to do this. Everybody loves mesh. Everybody knows how to handle this using mesh. The first thing is to write this. The second thing has nothing to do with this course. You need to simplify, extract, write it down in terms of a system, and then start solving it, right? So I1 is known. Where do I have on my I1? This one is 4, and I make sure it's going to be in the positive territory due to the intelligence that we took together. So let's take a look and see if we can actually simplify this. So I want I2 first and I3 next. Here's my idea. I2, I3 equal. I2, I3 equal. I need to have the same format for both equations. For I2, what do I see? I don't have any I2. I only have 1 minus. So I have minus 1. For I3, I have this and this. So for I3, I have 4 minus 3j plus 1. And then this is constant. This is minus, minus positive. It goes to the other side minus. So it's going to be minus 32j. I am surprised to see that many of us in the class have difficulty writing these equations in the form of a system. Please, this has nothing to do with my course. This is linear algebra. You need to make sure you can write it as a system and then solve it. You need to remember the Kramer rule. This is calculus 1, calculus 2. One knowledge builds upon another. You need to learn this stuff, my friends. So this is I2. I2 is 1. Then I2 is this. That's the second one. And I don't have anything else. I have I3, and I3 is going to be minus 1. I hope I haven't made any mistake. Hopefully everything is fine. Do I have a constant? I don't have a constant.
4.
Oh, 4, yes, this 4 is there, right? So this 4 is going to be multiplied by this, and I take it to the other end. So it's going to be minus 4 times 6 plus 8j. Okay, let me double check. I1 minus 1, I3 is this, I2 I2 is this, and I3 is that, and this one is constant, and this one is constant. Yeah, okay. Okay, that's fine. Let's get rid of this. Now, remember the stuff, a Cramer rule. Cramer rule says is this. This is going to be in the form of a matrix, minus 1. 4 minus 3j plus 1. You can simplify it. It's a very baby step to do, but you don't have to. 1 plus 4 is 5. 5 minus 3j. 1 plus 6 is 7. 7 plus 8j minus 1. What are the unknowns? The unknown would be I2, I3. I already know what I1 is. And equal to the right-hand side, minus 32j minus 4, 6 plus 8j. Again, some of us may go and do Gaussian elimination. That's a valid approach, but because it involves extreme human intervention, you are going to make a mistake. I don't want you to do that. Just simply say, give me delta. Delta is the determinant of this system. Minus 1, 5, minus 3, j, 7 plus 8j, and minus 1. This is called system determinant. What is delta x, or in this case, delta I2? Delta I2, remember this one represents I2? The first column is I2. In delta I2, the first column is replaced with the right-hand side. So it's going to be minus 32j minus 4, 6 plus 8j, 5 minus 3j, and minus 1. What is delta I3? I simply write it down. You see, you need to be calm. Just write it down. If you have practiced enough, all you have to do is to make sure you're doing it right in the first try. Delta I3, you need to replace the column. You see this one? This one represents I3, this one represents I3, this column represents I3. Replace this with the right-hand side. So it's going to be minus 32j, minus 4, 6 plus 8j, minus 1, 7 plus 8j, and that's it. Now we know what to do in terms of a 2 by 2 system. If you have A, B, C, D, the same principle applies. Diagonal minus anti-diagonal. So this is going to be AD minus BC. I need to multiply this minus this, this minus this, this minus this. Previously we discussed a 3 by 3 system. We might be able to discuss that today as well, but that's the way to do. Now, before you go and spend extra time, take an intelligent, smart step. You want to find VO. Well, in this case, actually, it happens to be the entire solution. Now, take a look at the VO. VO in this case is 1 times I2. You see, this is plus, this is minus. So take a look at VO. VO is equal to 1 ohm times I3 is coming in according to the Ohm law, plus on top, minus at the bottom. I2 is opposing it. So it's going to be I3 minus I2. Just write this down for a given problem. Why? Because sometime you will notice that you do not need to find all the unknowns. In this case, it happens that we do. But if you don't need to find all the unknowns, you can eliminate partial of the time-consuming process from the entire approach. So in this case, I do have to find them. So I'm going to go ahead and basically calculate the Cramer rule. The Cramer rule. Okay, the Cramer rule says I2 is equal to delta I2 divided by delta. Let's put that in. Delta I2, let's have the right side, minus 32j, minus 1. You have a minus sign anyway. 5 minus 3j times minus 4, 6 plus 8j. Did I simplify anything? No. I simply made sure I did that, because if I make a mistake at some point, I can actually see where that mistake is happening. This minus this. And the system determinant, you can actually calculate this once if you like to. Minus 1 minus 1, minus 5 minus 3j, 7 plus 8j. In order for me to utilize the calculator, I'm asking you to do this. This has a big bracket on top. This has a big bracket at the bottom, because those are the brackets you actually need inside your calculator. So let's take a look. I'm going to have a big bracket, this one, and then I'm going to follow bracket again, minus 32j, close bracket, times minus 1, minus open bracket, 5 minus 3j, times 4, times open bracket, 6 plus 8j, close bracket, close bracket. If you don't want to have too much, you can actually just do this first. Equal sign. You can actually do 1 at least. So in this case, it's going to be minus 216, and then shift equal sign, minus 56j. You could also divide it by this, but since I'm going to need this for the second one, I'm going to do that anyway. Let's do this. Erase this. This one. Open bracket, minus 1, crazy, times minus 1. Of course it's plus 1. Minus open bracket, 5 minus 3j, closed, times 7 plus 8j, closed. It's minus 58. And then shift equal sign, minus 19j. Let's calculate that and see how much I2 is. Okay, I'm going to inverse this. You have an inverse option, and that's the number, and then times open bracket, minus 216 minus 56i. So this is going to give me 3.6488, shift equal sign, minus 0.2297. Well, I went too far. Okay, let's calculate I3. I3, where am I? Okay, I need I3, so I'm going to erase this. Hopefully we haven't made any mistake on this. I3 is equal to delta I3 divided by delta. I'm going to check to see if I'm not missing anything, because I need a space. So if I follow that, it's this one, which I already know how much that is. And this one is going to give me minus 1, minus 4, 6 plus 8j, minus 32j, and then 7 plus 8j. I already know the denominator is going to be minus 58 minus 19j. Let's go on top and see what happens. Minus 1 times minus 4, of course that's plus 4, but still I'm doing it slowly by the calculator. 8i minus, open bracket, minus 32i times 7 plus 8i. Okay, that's minus 232, and shift equal sign, plus 256j. So how much is my I3? Let's divide that answer. I'm just going to have division because the answer is already stored in the calculator. Minus 58 minus 19j, and I'm done. This one is going to be 2.3066, shift equal sign, minus 5.1694. I make a joke and I say this is the time you need to go on your knees and pray that you get the same answer as you would get on the other two. So let's see if we do. That's going to be 1 times is exactly the same as the original value. That's silly, right? So let's go I3. 2.3066 minus 5.1694. That's I3. Minus, I need to be careful, I have a minus sign. 6488 minus 0.2297. Oh, J. Oh my goodness. J. Okay. I forgot the J. When you have shift equal sign, remember, you are getting the J part. Okay. So let's do that. This is I3 minus, stored already in my calculator, it's going to be 3.6488 minus 0.2297i.
Delta I2 is wrong.
The answer is wrong?
Delta I2 is wrong.
Delta I2 is wrong?
Yeah.
Okay. Let me go back and check. The matrix is correct though, right?
Yeah.
Okay. Well, it's easy to check now. Minus 32j times minus 1 minus open bracket 5 minus 3j times minus 4, of course, maybe that's what I forgot, times 6 plus 8j. Oh, that's a plus sign. And this is 120j. You see, it's really easy now to find where the mistake is, because the answers don't match this. My previous didn't answer, so I need to make sure where the mistake is. I need to actually go and very easily calculate everything and relatively fast. So I have that answer, division by minus 58 minus 19j. Okay. Okay, it's going to be minus 3.975, and then shift I do, minus 0.7667j. Let me see. That's going to be minus 3.975 minus 0.7667j. I need to multiply this by minus 1, of course, and then plus with these values, okay? Plus 2.3066 minus 5.1694. Well,
Those are the right values.
okay, let me try one more time. 2.3066 minus 5.1694 J. Okay, minus open bracket minus 3.975 minus 0.7667 J. Yeah, 6.2816, and then shift equal sign minus 4.403J. In this process, try to reduce as much possible the human intervention as possible, because the human intervention is going to cause a lot of mistakes in the process. It's really a heavy process, and the challenge is to do this in 20 minutes. Although there would be some easy questions to handle later, but obviously, generally speaking, that's the speed I want to see. And surprisingly, even today, while we are still away from the final exam, I can see people finishing 2 questions in half an hour, which means 15 minutes each. 20 minutes each, 15 minutes each. That's possible, that's doable, it requires practice. If you didn't get that answer, the same as the first 2 that you did, you remember the first 2? The first 2 is going to be your guiding post. You need to make sure the other one is going to be matching with this. You have someone helping you in the exam to achieve that, and that someone would be you, right? That's what the property of this exam is. The exam allows you to do a self-assessment right on the spot. And all you have to do is to practice. Okay, what is the last one? The last one says, find this using source transformation. Allow me to clean this. We have a few questions that we typically have to ask, but since the question says solve this using source transformation, it means those answers have already been answered. But take a look at the questions I need you to think of. Okay. That was 1, that was 4. Okay. Find VO using source transformation. The question you need to ask yourself is that, can I do source transformation? Which part can I do? What's the game plan? Is it going to help me or not? Well, remember the building blocks we talked about is this. You need to have a resistor in series with the voltage source. That's a Thevenin actually. If you have a current source in parallel with the resistor, then that's a library. This is a building block that allows you to go from one to another. You go from here to this, from this to this. So if this was E, I want to refresh your memory, that resistor still is going to be the same. This current is going to be E divided by R. Remember, if I imagine there is a short line, E falls across R, and if you write a mesh or a loop, it's going to be E divided by R. If you want to go from here to here, R is going to be the same, and what happens is this. If I leave this open, the current comes in, hits the top of the resistor, creating plus minus. That's how I'm going to get my polarity, and the value would be this value of the current times the resistor, which is going to bring me back the E. So that's the way I go from one to another. If I'm asking you to do Norton, you can always say, I'm going to find Thevenin, and I'm going to do Norton at the end. So whichever technique is suitable for you, you can actually handle it. Now understanding what the building blocks are, what is going to be helpful and what is not. I have a voltage source, I have a resistor, and these two are in series. That's me. I have a current source, and I have this resistor, and they are in parallel. Do I want to do this? Do I want to take this and make it a voltage source and a resistor? No. What's the game plan? The game plan is, I want to do source transformation so that this circuit at the end is a lot easier to handle. If I have everything in parallel, I'm fine. If I have everything in series, I'm fine. So what I could say is this and this. I'm going to take it. I'm going to process this and make it a kind of a Norton structure. And why? Because I have a current source, I have a resistor, complex albeit. I have a resistor, current source, resistor. Everything is in parallel. That's why it's going to be easy to handle. So I'm going to go in. So I'm saying is that you don't have to rush into doing a source transformation. This one is going to be a current source. How do I get this? Let me actually try to red, and I hope you guys can see the red for me. It's going to be a red. I don't know what the direction is. It's going to be a resistor. I know that resistor, a complex resistor. How is that going to be? That's going to be exactly the same as this. So this is 4 minus 3J. I just copied that, right? Now how much is this current? The value is simple. Voltage divided by that, that's the value of this guy. So the value is, let me write it down, the value is minus 32J divided by 4 minus 3J. That's the value. But what's the direction? I'm going to have an imaginary short line. An imaginary short line here. Because this is plus, the current goes through this and through this short line coming back. If I have the direction on this, I need to have the same direction to produce the same short response. Because of that, this is going to be going up, because it goes like this. When you have a short, all the current goes through the short line. The value I know, the direction I know, I can actually eliminate this and replace it by this one. I I can now handle this because everything is in parallel. Now, this is a current source, this is a current source. If you have current sources in parallel, you can actually shrink them. Now, first you need to verify if they are in parallel. This is a current source. The head of this current source, short line, head of this current source. The tail of this current source, short line, the tail of this current source. These two current sources are meeting head to head, toe to toe. Therefore, I can actually shrink this. Now, I want you to sit on this and take a look at your pocket. $4 coming to your pocket, and an imaginary dollar is coming to your pocket, right? Such as winning the lotto today, which is $640 million in US, right? So that's the imaginary number, is coming into your pocket. Now, how much is this number then? Because they are in parallel and they are both coming into your pocket, it's going to be the summation of both. That is going to be this one. What else can I say? I can see this are in parallel. I need to find this voltage. If I do a circuit reduction, still the voltage is accessible to me. My point of attention is still accessible to me. So I'm going to say, why don't you give me all three in one resistor and then have one current to go in. The value of the current is simple. 4 plus minus 32J divided by 4 minus 3J. I hope you remember the similarity of this number we did find in nodal mesh analysis, right? How much is this? You remember we already done that. 1 over Z equivalent is equal to 1 over 4 minus 3J, 1 plus 1, 1 over 6 plus 8J. I find this and I invest it. I did that already, so you can actually take advantage of that, saving yourself a bit of a time. What am I looking for is this voltage. Okay, let's do it. Let's find the Z equivalent first. I'm going to do 1 divided by open bracket 4 minus 3J plus 1 divided by 6 open bracket 6 plus 8J. Whatever it is, I'm going to inverse that because I need Z. Inverse that. And whatever that inverse is, I need to multiply it by this. So I'm going to multiply. I didn't even write it down. Of course, in the exam, please do, because we want to see the steps you have gone through so that you got to the last stage. But you can always do that when you want to do the test. 4 plus, open bracket, minus 32J divided by, divided by, open bracket, 4 minus 3J, close bracket, and I hope and pray to have the same answer as before. Yes, I do. Yes, I do. VO is equal to 6.282, shift equal sign, minus 4.4026J. You have a light in the exam, a guiding post in the exam. Find a solution accurately and use that as your guiding post. Don't go back to that one. The one that you feel comfortable. And for example, this one, we solved 4 questions, the most difficult questions in about 1 hour and 10 minutes. 1 hour and say, worst case, 15 minutes. So 4 times 20, how much do you get? 4 times 20 is about 120 minutes. And we did it, 4 times 20 is 80 minutes. 4 times 20 is 80 minutes, and we did it right almost 80 minutes. Actually, less than 80 minutes. We finished it. So as soon as you finish this, you feel good. You feel good, and you go and you do the rest. The rest shouldn't be taking you too much of a time. Now, remember though, the last thing we forgot to do, and to take this to the time domain. You do it only once. Let's do this to the time domain and see what happens. And remember, in the class, right now I have been explaining things that I didn't need to explain. And I was talking, and I didn't have to talk inside the exam. So obviously, if I'm prepared, I should be able to do 4 questions in less than an hour time. In order for me to take this to the time domain, I need to punch it in and then go into the polar representation. So let's go take a look. I'm going to have 6.282 minus 4.4026J. That's my complex number. Then, if you take a look at this specific value, on top of the plus, you have a polar representation. Shift plus equal sign. So that's going to give me 7.67, and then shift equal sign is going to give me angle minus 35 degrees. So this is going to be, in time domain, of course it's not equal anymore, 7.67 cosine. We made an agreement. All the signals are in cosine format. Open bracket, you remember the omega, 40 minus the 35 degrees, and that's the answer you would get. Okay? Let's go into question number 5. I'm going to solve question 5, 6, 7, 8, and 9, and then I'm going to give a break. Is that all right? Everybody's fine? Okay, let's do it. Question 5. Okay. Question 5 is all resistive. It's about maximum power transfer. It's going to be 2 ohm plus minus 10 volt. The resistor of attention, the load R, 3 ohm plus minus 20 volt, 5 ohm, and 6 amp. Hopefully I copied properly. If you do have time, go back and make sure you copied the system correctly. Well, we want to find the Thevenin, and after we find the Thevenin, we want to know what is R in order to have the maximum power transfer. Now, in order to answer this question, remember the load is behind you. You take the load out. You take the load out, and you are supposed to find the voltage across the load. This is where the load sits. I took it out, and I want to find this voltage. I want to see the Thevenin from terminal A and B. Terminal A, terminal B. I want to know what the Thevenin is visible from terminal A and B. Well, if you remember, for Thevenin, we had so many different techniques. Find V open, find R equivalent, you've got yourself a Thevenin. Find I short, find R equivalent, you've got yourself a Norton, which is a twin for Thevenin anyway. So, V open, R equivalent, I short, R equivalent, and if you have no choice, there are possibility that you can't basically find R equivalent because they involve Y or delta, and we didn't talk about them in the class so far. So if that's the case, then you need to find V open and I short. V open, I short, V open, R equivalent, I short, R equivalent. You've got yourself the equivalent design visible from A and B. This is relatively easy. The first thing I need to do is to find R equivalent. That R equivalent is visible from terminal A and B. All I have to do, everything is DC. I have to shut down everything. Everything is DC and everything is independent. I'm sorry, yes, independent. So if I do this to the ground, that's going to be a short line. Allow me to use a red one so that you know what I'm saying. This is a voltage source and it's going to be a short line. This is a voltage source and it's going to be a short line. This is a current source and it's going to be an open line. I want to remove it to the last molecular because if I do, you would see a different one. For some reason, our brain is wired to see things differently. If I have this wire, it's just open, right? So that's what I'm going to do. Now remember back then, at the early days of this class, when I said that you are supposed to identify what are the components in series and what are the components in parallel. Now you need to identify that very fast because you want to have time to come back and check question number 1 to 4, right? So you need to identify this very fast. I want you to grab this A and B. grab it out and then shake it for me. When you shake it, you can see 5 and 3. Remember, this is a rubber band. 5 and 3 are in series. That's your 8. And then it's 2. Let me go slowly. This is A and B, and you have 2 on top, and then you have 5 and 3 at the bottom, and that's 8. As I told you, grab this and shake it. If you do, you can see 2 and 8 are going to be in parallel. 2 and 8 are in parallel, therefore R equivalent is equal to 16 divided by 10 or 1.6. You can do either rule of G rule for 2, or you can do the multiplication of 2 divided by the summation of 2. And remember, that second one is only applicable for the 2 resistors in parallel. I've got myself R equivalent. I've got myself R Thevenin. Okay. Let me go back to my original design. Original design, 20 volts. Let me put it back in, 20 volts. 10. And then 6. Just a step back one more time to see if the direction, polarity, everything is fine. Yes, it is fine. What am I trying to do this time? I found what R equivalent is. I found what R Thevenin is. Okay. I want to know how much V open voltage is. Open voltage. I say open, which means there is no load, which means there is no current that goes in. So these are the property of an open line. Well, you have a bunch of techniques you can do. You need to find this voltage versus the ground, this voltage versus the ground, subtract that. I want you to sit back for just a couple of seconds and make the smart decision. Do you want to do nodal? Because if you do nodal, are you facing a simple nodal equation or are you facing a supernode? Of course, you can rearrange your stuff and make sure you get a simple nodal though. I challenge you to see this as a simple nodal. I want you to see it. It's really a simple nodal. But if you can't see it, give you a hint. If you switch this over, and if you switch this over, the 2 voltage sources are actually meeting here, right? If I put this as my ground, then it's a simple nodal, very simple nodal. These are the things you have to see before you start punching your fist on the question. You need to make a smart move. Okay, but let's say we don't see it. If I do this ground, this is going to be supernode. It's going to cost me time. Okay. Do you want to do superposition? No. 3 sources, it tells me 3 different sources. And that's really too much. Then perhaps I want to do, you can do source transformation. Once again, I challenge you. This is not really that bad. You can even do source transformation. You can do this source transformation, give you a voltage and a resistor, and that voltage and a resistor on this side, you can shrink this part. Do you see this? And then you have voltage resistor here, and you have voltage resistor on this side. How can you handle that? You do one more source transformation on top and the bottom, and it gets you current source on top and resistor in parallel, current source at the bottom and resistor in parallel, and you shrink them all. And then it gives you a Norton, you do one more, and you come back. So you have plenty of opportunity. But another option is just to simply go and do a mesh. What I'm asking is simply find the convenient time for you to solve this. I'm going to see, because this is open, I have only this loop, and I have this loop. How many loops do you have? 2. How much is this current? You're touching this once, and therefore this current is already, let's actually label this with a small case, it's 6 amp. So how many equations do you need? 1 equation. So far, you have to write the KVL for this loop. It's going to be minus 20 plus, let's call this I2 for now. It's plus 3I2 plus 2I2 minus 10 plus 5. And I have 2 currents that go in. I2 is the master. I1 is a slave, and it's opposing, and it's equal to 0. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 terms. And I know I1. I1 is actually 6. Let's solve this. This is minus 20, minus 20. Hopefully we did it right. It's okay. 3 and 2 is 5. 5 and 5, 10. So I have 10 I2 safely. Then I have minus 20, hold on. Minus 20 going the other side plus. Minus 10 going to the other side plus. 5 times minus 6 is minus 30 going to the other side plus. So this is going to be 10 I2 is equal to 30, 30, 60. I2 is equal to 6 amp. First, you solve the system. I solve the system meaning that at any time, if I want to find any current and voltage, I can now identify it. How much is this current? I know that. How much is this current? I know that. How much is the voltage across this? I know that. So I have solved the system. But I haven't found V open yet. There is a simple trick for that, and I want you to watch me as to how I'm going to achieve that. Now, this is a broken line. A broken line is a 0 amp, right? So I want you to put an amp, the current in, and the current, for example, goes this way, and let's call this current I3, and its value is 0. I want you to put a 0 current in. Since I'm looking at this loop, I have this loop, and this loop, if I go, doesn't matter which way I go, if I go this way, this current source is touching this, and therefore this current is actually 0, because it is going through an open line. Do you see this one? It goes through an open line. I want to remove this for now. I want you to take a look at this, please. Okay, I want to remove it. There is a loop. You can see that loop. That loop involves the broken line. The voltage across the current source is VAB. That's the voltage I want to find. That's the voltage I want to find. Let's go by this loop and write the KVL law for this. VAB, A, B, as I move from this direction. Then plus 10, then plus 2 times I3. Let's call this I3, please. I3 is the master. I2 is the slave. And as I3 goes this and I2 goes this, it's a minus sign is equal to 0. VAB plus 10, 2 times I3 minus I2 is equal to 0. So this is going to be VAB is equal to, I know what I2 is. I2 is 6. 6 times 2, 12, minus 12. Minus 12 and 10 is minus 2. It's going to be 2 volts. Another way of doing it is obviously to say VAB. Another way of looking at it. Again, this is all a visual context. How do you see this? Okay. Another way of looking at it is this. This is in parallel with this. Right? This is in parallel with this. This voltage is the same as this. So if I find this voltage, I found this voltage. I didn't assign any current yet. Right? So I'm going to say 2 times I2 minus 10, this is the voltage. 2 times I2 minus 10. 2 times, the only thing that goes in now is I2. Minus 10. It's this voltage. This voltage is in parallel with this. I found it. You can see this, and you can find it. 2 times 6, 12 minus 10, that's 2. You got yourself. So what did you find so far? You found a V Thevenin, 2 volts. You found an R Thevenin, 1.6 ohm, and then you are ready to bring in your load. We have shown and proven to you in the class and on the YouTube that in order to achieve maximum power transfer, and you saw it in the lab, the maximum power transfer happens when R is equal to R Thevenin. Well, that's going to be 1.6 ohm. Then, suppose you forgot the equation for the maximum power transfer. All you have to do is this. How much is the current going through this? How much is the voltage? Because the resistors are the same, this voltage is half this. Or in front of one voltage source, excuse me, the smell of this. So basically these two are the same. This one is going to be half this voltage. So your V out is going to be 1 volt. Your I out is going to be 2 divided by 1.6, 1.6, right? And then VO times IO is your P max. That's one way of doing it. Another way of doing it, P max is equal to V Thevenin to the power of 2 divided by 4 R Thevenin. Okay, so remember there is no formula sheet for this. The concepts we are dealing with are extremely basic. Of course, if you have calculus 1 and 2, you might need to have a formula sheet, but not in this course. So please have that in your mind ready. Okay, let's go. And this one we finished it in 15 minutes with all the explanations and all the different solutions and everything. So you can see question 1 to 4 is the major one. If you solve that, then the rest is going to be an easy save. Let's take a look at the question number 6. The Wheatstone Bridge. This time it's going to be, the Wheatstone Bridge is just a formation. There are purposes for this. When it is balanced, we draw conclusion, but generally speaking, it's just a topology. It's nothing really confusing about the name or the topology itself. You simply devise a technique and go ahead and solve it accordingly. Okay. I have, someone gave me minus 5J. Then I have 13 ohm. Then I have 10. I have this open, A and B. 12. If you are copying it on your exam paper, make sure you copy this correctly. At least quickly before you begin solving it, verify that you have copied this properly and correctly. Okay, this is a voltage source. And that's 60 angle 45 degrees. Okay, let me double check. I have 13 minus 5J, 3J, 8, 12, and 10. Yep. I can also verify something. This is inductor, it's supposed to be positive, it is. This is capacitor, it's supposed to be negative, it is. So, perhaps the examiner might have made a mistake, and that's where you can actually come in and fix it. Just write down, I think this has to be negative, you gave me positive, I'm going to start solving this by a negative number. What's the question? The question is, find the Norton from point A and B. Well, you can do Norton, as I said, you can do Thevenin, and then the final step would be a Norton. I want to do Thevenin because it's really easy. This one especially is extremely easy. We have had variations of Wheatstone Bridge. Variations of Wheatstone Bridge. This one, this one, okay, and then you could have a current source. That's one. You could have this shape, okay, and you could have a voltage source, and then you could have the point of interest here. You could have this one, current source, this one, and then this one, and then the point of attention would be this one. These are all variations of the Wheatstone Bridge. I want you to find Norton or Thevenin from this, Norton Thevenin from this, Norton Thevenin from this point. Nothing should surprise you. It's not really difficult to do this any other way. Okay. Let me go back to my original design and make a decision as to what I'm going to do. Well, this is a voltage source. If I shut down this to a 0, and I have seen this pre-midterm, if I shut down this to 0, that's going to be a short line. If I grab this to in my hand and take it off the space and shake it, if you grab this, or if you draw this on a piece of a paper and then fold this, right? If you fold this, because this is a short line, you can see that the folding happens and these two ends are going to meet. I can see what's happening. I can see this in parallel with this in parallel with this. The outcome is in series. That's doable, right? I want to find VAB. Because I have a voltage source, if I assume this to be my ground, I know what this voltage is. If I have that voltage, all I have to do is do one nodal to get VA, one nodal to get VB, and VAB is VA minus VB, right? So if that, you see, you need to devise that strategy. If you do, it's fine. Another warning, the exam is 3 hours, and by the time you get to this stage, your brain is tired. Unless you are automatic by that time, you're going to lose it. Which means that you see it, you just make your mind, you go ahead, you do it, and then you have time to come back. The exam is supposed to generate a lot of heat on your mind. So please exercise. Exercise, that's the only reason for success. Okay, let's find Z Thevenin. In order to find Z Thevenin, I'm going to see this as one block. It's 13 minus 5J. I'm going to see this as one block. That's 12 ohm, of course, just one resistor. That's another block. That's 10. And another block. That's 8 plus 3J. Now remember, I'm going to shorten this one. I'm trying to find Z Thevenin visible from terminal A and B. Whatever Z Thevenin is applicable to both Thevenin as well as Norton. So let's do it. I want you to fold this. When you fold this, it's A, it's B. You have an original 8 plus 3J. You have an original 10. But what happens is that when you fold this one comes in. This one comes in. That's your 12. That's your 13 minus 5J. Okay. So what is my ZAB? My ZAB is the parallel of these two guys. I'm going to write it down. 10 in parallel with 13 minus 5J plus, they are in series, outcome, 12 in parallel with 8 plus 3J. We haven't spoken of this officially, but if you do have two resistors, only two resistors, remember please, it's not available for the general case. Z1, Z2, Z equivalent for two resistor is going to be Z1 times Z2 divided by Z1 plus Z2. If you have three resistors, you can't do it. You can do two at a time, but you can't do it as all at once. You need to follow the G rule. So let's take a look. This one tells me it's going to be 10 times 13 minus 5J divided by 10 plus 13 minus 5J. 12 times 8 plus 3J, I'm writing it down. I'm not rushing. 12 plus 8 plus 3J. I hope I didn't make a mistake. I simply go in and find and do the calculation. Let's do it. On top, I'm going to have 10 times open bracket 13 minus 5J. That's on top. Divided by. I need you to put this in the entire bracket, or you can say 10 and 13 is 23, right? So whatever comforts you, I hope you can add them up. I'm not surprised if you say 10 plus 13 is equal to 3, because it's an exam time. But you can put them all and be careful about that. 23 minus 5J, that's this guy. Plus, let's do this part. 12 times open bracket 8 plus 3J, that's on top, divided by 12 and 8 is 20. So it's going to be 20 plus 3j, close bracket. Nice. So this one is going to be 10.8068 real part. Shift equals sign. I am conscious about plus minus sign this time. 153.7j. Did you guys get the same answer as me? Hopefully, I didn't make a mistake. So basically, this, and I'm done. 2 resistors, 2 overall components in series. Now, I want to find VA, I want to find VB. In order for me to find VA and VB, I just need to remember the bridge. I just need to do a nodal for A and a nodal for B. It's going to be, this is my ground, this is my reference node. Reference node. If this is reference node, that's going to be 60 angle 45 degrees. You are going to have a question similar to Wheatstone in the final exam, but of course the topology is going to be different. I appreciate and encourage you to pick up 4 different topologies I just presented to you and try to solve them both individually, as a team, and then check the answers I have posted on the Blackboard. So it's going to be VA minus 0 divided by 10. VA minus top, 60 angle 45 divided by 13 minus 5j is equal to 0. 13 minus 5j is actually inside a bracket. I'm conscious about this. Let's do the VB. VB minus 0 divided by 8 plus 3j inside the bracket. VB minus on top, 60 angle 45. And I know this is a degree, and I'm happy that my calculator by default is in degree. So I'm very conscious about that too. Divided by 12 is equal to 0. Okay. Okay, let's solve this. Because there's nothing else I need to do with this circuit and I am short of a space, I'm going to erase it, assuming that I have copied the numbers correctly. Okay, let's do the VA. VA 1 over 10 plus 1 divided by 13 minus 5j is equal to, take this to the right hand side, 60 angle 45 divided by 13 minus 5j. Try to minimize human intervention in this process. As much as you can, of course. If not, then you have to. So this is going to be 1 over 8 plus 3j, 1 over 12. Take that to the other end, 60 angle 45 divided by 12. Hopefully I did everything right. So I need to find VA. Okay. In terms of a strategy, you can calculate this, inverse it and time it this one. You can calculate this divided by this one. Whatever you do, you exercise, you get used to it, you get sync with the process. So let's do this one. 1 divided by 10 plus 1 divided by open bracket 13 minus 5j. This guy. I'm going to say equal sign, and I don't have to write whatever it is. Of course, in the exam you do, but not now. I need to inverse that. Just do inverse. It's going to have a real part, it's going to have an imaginary part, and then I need to multiply by this. But that's a polar number. You see, it says answer multiplied. Answer is a complex number. Now, polar number, I do have the luxury of a polar number at the very same time. Take a look at this, and on top you see an angle. So I'm going to say times 60 angle. Take a look at this, shift minus sign, angle 45 divided by open bracket 13 minus 5j close bracket, and you're done. This one is going to be So I did calculate this, I did inverse it, and I multiplied it by this. I hope I did inverse it. I'm going to check that in a moment. 13.7847, and shift equal sign is plus 21.44 J. Am I right? So I did inverse. Okay, thank you. Let's do VB, so I hope I am able to do the same thing. I need to calculate this. 1 divided by 12 plus 1 divided by, open bracket, don't forget the bracket, open bracket, A plus 3 times I. That's my number. And then when I say equal, it's going to be an answer. I'm going to do inverse. As soon as I do inverse, I say equal, I got it. Right? That's the inverse. I inverse this and I need to multiply by this guy. So let's multiply. You have a polar at the same time. Don't panic, it's a polar. So it's going to be 60 angle, which is this guy. And the angle is 45, and the mode is in degrees, so I'm safe, divided by 12. Even 12, I put it in the bracket. A silly thing to do. Okay, equal sign is going to be 13.796, and then shift equal sign is going to be plus 21.265 J. What am I looking for? I'm looking for VAB. VAB is equal to VA0, which is the reference node, minus VB0. This is 0, this to this to this in my original design. So, okay, this one, well, let me go from the first 13.7847 plus 21.44 J minus 13.796 minus, remember this is inside the bracket, the entire thing is minus VB, so you need to be very careful on that. 265J, and you've got yourself minus 0.0113, almost 0, and then shift equal plus 0.175J. Am I right? I hope I'm right. Okay. But at any cost, I can always go back and basically check this. Again, I finished this with all the explanations and all the variations in 15 minutes. You can see I have so many.
We want the Norton, right?
Sorry? Oh, I need the Norton. He's right. The question is asking for the Norton. So, okay, what did I find so far? The polarity, 0.113 plus 0.175 J, and I've got myself the Z equivalent, and the Z equivalent, and the Z equivalent was sum. Okay, I'll leave this to you guys, anything. So this is going to be the Z equivalent. I missed it already. You already have it. So this divided by this is going to give you the current, and the current has to go up, and you copy the Z equivalent, and you've got yourself a Norton. Okay, so that's question number 5. I'm sorry, question number 6.
We take a break before we do ours.
Okay, let's do a break, and then we'll come back for question 7 and 8.